Good morning. I'm Kerry Emanuel from MIT. I'm here today to talk to you about the problems of climate change, focusing on the ethics, some of the ethical considerations of it. So without further delay, I'm going to share my screen and talk to you about climate science and ethics. So climate change is one of quite a few global problems that we constantly have to worry about. It's not a particularly interesting or surprising point. We have climate change, we have energy, and we've seen some of the problems with the production and transmission of energy in connection with the conflict in the Ukraine. And then we have global poverty, which is a very serious ongoing problem, and the problem of population and population growth. My thesis is that these four problems are very tightly interwoven and should not be decoupled. They're often talked about separately, but in fact, there's a very strong interdependence. And I want to spend some time talking to you about that today. But to do that, I first have to talk to you about something a little bit more elementary, which is the concept of risk and the very closely related concept of responsibility. This is a bit of ethics 101, but I think it's useful to review that here. I'm going to do that by starting with a kind of real world example. So bear with me and try to do this thought experiment. Supposing you're in charge of a little girl, like the one shown in this picture. She might be your daughter or a friend's daughter, for example. And in particular, you're in charge of getting her to her school bus on time, but you're a little bit late and the bus is waiting across the intersection and you're faced with a choice. You can let the little girl run to catch the bus, but then she risks being hit by a car. Or you can take her to school in your car, but that will cause you to be late for work with some ramifications. So what does your decision tree kind of look like? So it's useful to separate things out into first what we call the event probability. What's the actual probability that something will happen if she's allowed to run? Now, this is a binary decision, which is a relatively easy one, not to say that it's easy in an absolute sense. She either stays or she runs, okay? If she stays, she's not going to get injured with 100% probability. But if she runs, there's still a very high probability she'll make it. It might be 99%, but there's some probability she'll be struck by a car, injured, or God forbid, killed. So that's what we call the event probability. Then there's the cost to this. So if she stays, she doesn't get injured, but you may lose something for being late at work. So there's a cost to you of doing that. If she runs, okay, and she doesn't get injured, there's no cost to anybody. In some sense, that's the most desirable outcome. But if she does get injured, that's a very high cost. And if she gets killed, that's almost, to most people, would be an astronomical cost. So that's sort of the things that go on mostly unconsciously in our head when we're confronted with a situation like this. The first thing, the event probability, is a matter of math and physics. What are the probabilities that she's going to get hit by a car? The second thing that costs is something that belongs to social science and economics. How do we attach a number to the life of a human being, for example? It's very tricky stuff. So there are all kinds of things that introduce uncertainty into this problem. But the important concept here, which is part of the definition of risk, is what you call the expected cost, is the probability times the cost. So for each of these outcomes, you multiply the probability times the cost of it, and then you sum over all the possible outcomes, and that gives you the expected cost. So there's a very, very small probability that she's going to get killed, but it's an enormous cost. So the multiple of these two things actually contributes or can contribute substantially to what we call the expected cost. And what we're trying to do in some sense is minimize that, okay? It's not too complicated, but when you actually try to apply it in the real world, it can get quite tricky. And this is still a binary decision. There are just two possibilities. In real world cases, besides something relatively straightforward like this example, there can be a continuum. Now, complicating all of that is human nature, and particularly the influence of what you might call priors, assumptions that you might have made consciously or unconsciously. And in our example of letting the little girl run or not run to catch your bus, I'll come up with some possible priors. Well, you can say, I've never heard of a pedestrian being run over at this intersection. So that's going to bias you toward letting her run if you think that. There's never been any serious accidents in my family. This is kind of an irrational one. It says, well, nobody's been hurt so far, so it's unlikely they're going to get hurt now. But people do sometimes think that way. But if my daughter doesn't get to school in time, the teacher might lower her grade. Maybe she won't get into college. I hate being late for work. I might get penalized. So these are examples of subjective things that might influence a decision in a way that's not going to simply minimize what we call that cost function that I talked about before. All right. All of these things are at work in decisions we make about really important global problems as well, even though this is just a local example. So we can use this in a way to think about why the climate change problem has proven to be so difficult and intractable in some ways. Well, the decisions and the costs are continuous. There's lots of different things. You can lower your carbon emissions by any amount, okay, up to eliminating entirely. It's a continuum. It's not a binary decision at all. The event probability, the probability that something bad will happen, terrible storms or droughts or heat waves. We in climate science know that when we try to estimate those, even for the current climate, but especially for a future one, that these have large error bars. So estimates of probabilities are uncertain, as are estimates of costs. So the cost of trying to do something to mitigate the situation by, for example, turning to a different source of energy or adapting. Those costs have large error bars too, all of which contribute to the uncertainty in trying to minimize that cost function. Now, here's something that's not at play in our simple little example, is that the costs of not doing anything about this at all are borne mostly by future generations, or at least people think that they will be, okay? So there's a temptation to just pass the buck. And so we have, in addition to that, the pernicious influence of priors in this problem, just as we did perhaps in my thought experiment for the little girl. But I'm going to come back and talk about what I think those priors are in a while. So let me now turn to just a very quick review of climate change and climate risks. And just so that we're all on the same page, I'd kind of review some of the most elementary evidence for it, which dates back to the work of Svante Arrhenius, who was a Swedish chemist who won a Nobel Prize, but like many scientists of that era, dabbled in other projects, and he was the first that we know about to be concerned that our consumption of fossil fuels might raise the carbon dioxide content of the atmosphere, and that might change the climate. And he wrote in 1906 that if one were to double the percentage of carbon dioxide in the air, that would raise the Earth's surface temperature by about 4 degrees. And, that's remarkable. He did this with elementary physics, obviously no supercomputers, just plain physics of radiative transfer, convective heat transfer, and other things. And after all the intervening years and huge calculations, what we really succeeded in doing is putting error bars on his estimates. So the modern estimates are between 2 and 4.5 for doubling CO2. Was he right? Well, let's have a look at this. Here's the record since the time of Arrhenius of the global mean surface temperature of the Earth in blue, okay, every year. And in red, the natural logarithm of the concentration of carbon dioxide. The radiative effects of CO2 go very nearly as their natural logarithm. And so you can see that, of course, the temperature has a great deal of variability, ups and downs. All sorts of things are happening besides greenhouse gas warming. There are volcanoes, there are changes in solar output, and so forth. But by and large, you see that Arrhenius's prediction was pretty good. And the message here is that the physics behind the idea that we're warming the climate, as well as the observational evidence, is really, really strong, all right? That doesn't mean that we can quantitatively predict the future accurately, but the notion that we're changing the climate is on really, really good grounds scientifically. Carbon dioxide is the most important long-lived greenhouse gas in the atmosphere. And we know from paleo data that it has a pretty strong correlation, in some cases a controlling one. But this is a record from an ice core of CO2 concentrations going back 800,000 years on the left side of this diagram. So this is CO2 concentration. You can see it going up and down, and it turns out it's going up and down in phase with the global mean temperature, although in this particular case, mostly it was the temperature causing the CO2 to change. But my point is that, by and large, we had CO2 levels between 200 and 280 or so parts per million. And that spike, that black spike you see in the far right side of this, is what we have done to the carbon dioxide concentration. That blue star is approximately where it is today. I have to keep moving that one up practically every time I give this talk. There's no question that that's what we've done. We know from looking at the isotopic concentration of carbon dioxide that the CO2, this excess CO2, is carbon that's been put up there from the combustion of fossil fuels. Now, projections in the future, of course, are very difficult because, among other things, it depends upon what we do. But here's a set of projections of the concentration of CO2 out to the end of this century. And they range from something like a doubling of CO2. This is the blue dash line, represents double the pre-industrial concentration of CO2, all the way up to something closer to triple that concentration. Well, you can't take the most important long-lived greenhouse gas and change it by order one and assert that there will be no risk in doing that. The question is the level of risk. So what are the risks? Well, the most important thing to tell you about this is it's not that the world is warming up. In fact, we've been very remiss as climate communicators in stressing this. It's because this is one of the most robust numbers we can measure is the reason we talk about it. But nobody really cares about whether the world's going to warm up 3 to 5 degrees. I don't care. I can get that by moving from where I live in the state of Maine down to the mid-Atlantic states. That isn't it. The thing that we are concerned about and should be concerned about are extreme rare events and how their probabilities change. That's what really gets us in the end. It isn't the global mean temperature per se, but it can serve as a proxy for the probability of these extreme events. Now, why is that the case? Well, it's pretty elementary in the end. Why is climate risk dominated by extreme events? And if you stop and think about it, that's just common sense. Societies are usually well adapted to frequent events. In a place like Boston, a 30-mile-per-hour wind isn't going to cause any damage, all right? And it happens all the time. Societies, on the other hand, are often poorly adapted to rare events, extreme events. A 100-mile-per-hour wind in Boston is very rare and would cause a great deal of damage, much more in some proportional sense than 100 miles per hour would do in Miami, which is a bit more used to events of that magnitude. So we get into trouble if there's a change in the climate that results in events that were once rarer than once in 100 years, becoming much more frequent than that. And why is 100 years special? This is just a curve. It's not from actual data, but it reflects lots of curves like that. It's the percentage of property destroyed versus not the magnitude of event. It could be an earthquake, it could be a volcano, it could be a windstorm, a wildfire, but the return period associated with that magnitude of the event. And this is almost a universal curve, almost independent of what phenomenon you look at and what kind of society you look at, as well as long as it's been around for a while. So the steepest part of that curve is about 100 years. So what's magic about 100 years? I don't know. I think that's an anthropological question. I suspect it's just a few or a handful of human generations. It's like a human cultural memory timescale. So it's these rare events. And okay, well, what are the risks? They're increasing sea level. And that's especially true during storms, where you get storm surges like the one that accompanied Hurricane Sandy in New York in 2012. Another risk, which is very important, is increasing hydrological extreme events, which include both droughts and floods. And it's a matter of simple physics that both of these tend to increase as you warm the climate. An increasing incidence of high category hurricanes, even though the far more numerous weaker ones might actually decline. And then the associated phenomena of storm surges and freshwater flooding from torrential rain. That, by the way, is my own field, is tropical cyclones. More heat stress and other health risks that are associated with high temperature. And this is a big one, at least in my book, the potential for particularly shortages of food and water to lead to armed conflict in a world which has nuclear arms. And it's something that our own Defense Department worries about a great deal. Now, there are benefits too, which have to be figured into the calculation. There's some increase, at least initially, in plant productivity just from having more carbon in the atmosphere. It's limited, becomes limited then by limited supply of nutrients. It's a very interesting problem. And there should be a reduction in health problems that are related to cold weather. But if you look at the sort of sum total, anytime you change the climate away from what we're adapted to, you're going to have problems. It would be true if the climate were getting colder. So the Intergovernmental Panel on Climate Change, IPCC, says, taken as a whole, the range of published evidence indicates that the net damage costs of climate change are likely to be significant and to increase over time. It's very interesting about hydrological extremes. Rainfall intensity is really just limited by how much water vapor is in the atmosphere. And that scales with something called the Clausius-Clapeyron equation. It goes up exponentially with temperature, doubles approximately for every 10-degree C temperature change. But there are hard limits on global rainfall. And so the increase in intensity of rainfall has to be compensated by longer intervals between when it rains. And the net result of this is that places that are already wet tend to get wetter, places that are already dry tend to get drier, and places that have some rain but not a lot will see heavier rain but more rare rain storms. And the result of that is that, ironically, you get an increase in both the incidence of floods and droughts. And the problem with that, as I mentioned before, is that it has a large potential for affecting the supply of food and water, and that plays into national security because that tends to be very politically destabilizing. And so in its quadrennial defense review, the US Department of Defense says climate change could have significant geopolitical impacts around the world, contributing to poverty, environmental degradation, and the further weakening of fragile governments. Climate change will contribute to food and water scarcity, increase the spread of disease, and may spur or exacerbate mass migration. Now, this is the Defense Department, okay? It's not a bunch of hippies saying this. It's a very serious organization, and they regard climate change as one of the top national security risks. Other governments feel the same way about it. Now, I'm going to give you a very specific example to illustrate some points about climate risks, which is the example of hurricanes. Since 1971, on average, about 10,000 people a year have been killed by hurricanes, and $700 billion US dollars in damages have been done globally since about 1971. And a really worrying thing, thanks to demographic trends, is that the global population exposed to hurricane hazards has tripled since 1970. Everywhere you look, people are moving from fairly low risk places to pretty high risk places like coastal areas. And you can see this in hurricane damage. And here's a chart going from 1900 to more or less the present of the total amount of damage done globally by tropical cyclones each year as a fraction of the world domestic product. Okay, so this is a normalized measure. It's kind of inflation proof. You can see there's been a big increase, 380% increase since 1970. And a lot of this, most of it, maybe almost all of it, is driven by the population increases in places that are prone to hurricanes. And that's estimated to have gone up by about 200%. But the difference between those two numbers suggests that maybe there is also a contribution to climate change, although that would be difficult to prove. Now, to give you a more specific example, let's talk about the calamity that happened in the part of the developed world. Well, I think it's the developed world, although I have reservations about Texas. This is Hurricane Harvey, and you're looking at an aerial photograph of a neighborhood in Houston, Texas. Now, interesting that within a few months of that storm, there were 3 independently conducted studies, of which I was the author of one, that all said that the probability of the rainfall that caused that flooding in Hurricane Harvey had increased somewhere between 4 and 10-fold in the last few decades. My study was based on modeling. One of the other studies was based on historical records. And a third study used both observations and models, but we didn't know about each other at the time. We came to very similar decisions. These are huge increases. They're not just a few percent, they're several 100%, okay? And that's what happens in the wings of the distributions. It's the rare events that are the canaries in the mine, if you will, for climate change. Now, the problem is if we want to try to estimate the risk of these hazards, and this is the way it is currently being done for the most part by the insurance industry, for example. We have to have enough history to have a good idea of what the 100-year event is. That's what we're worried about. That's a big contributor to damage. Well, typically, we don't even have 100 years of records. Maybe just about, really to do a good job with a 100-year event, you probably ought to have 1,000 years of data. Nobody's got that, okay? We might have 100 years for riverine floods, flash floods, and tropical cyclones, less than that. And this is in the US, by the way. But, and this is a big, big but, as we can see from the results of Harvey, even if we had 100 years of great records or 1,000 years of great records, the problem is that they're no longer a good guide to the present, let alone the future. And this is something the insurance industry has recently woken up to. They used to say they didn't care about climate change because they're writing one-year contracts, but they realize that those contracts are based on risk assessments that are based on the last 50 to 100 years, which are already a poor guide to extreme events that are occurring right now. So we have to turn away from historical records and toward physical models to get better estimates of weather risks. And I could give you a long song and dance about that because I spend a lot of time on it. But the notion is that we're going to actually bring physical modeling. What are physical models? They're models such as those used today routinely to predict the weather. They're just algorithms for solving the known equations governing the physics of the hazard. So I'm just going to show you the outcome of one such risk estimate without telling you all the details. And what we have done is we have generated about 6,200 synthetic hurricane events affecting the eastern U.S., downscaled, and the downscaling has an awful lot of physics and stuff behind it. I don't have time to describe it, but downscaled from 8 global climate models for 2 periods of time, an historical period, 1984 to 2014, and a future period, 2070 to 2100, assuming a kind of middle-of-the-road emissions estimate. So for each of these hurricane events, we calculate the peak wind experienced at the centroid of each zip code in the eastern United States. All right, so we have 6,200 events. from two time periods, each from 8 models. So you're going to multiply 6,200 by 8 by 2. That's an awful lot of events. Then we're going to use a damage function to convert peak wind to percentage of insured value destroyed. All right, so wind destroys property. It's a very nonlinear function. I won't go into it now. And we're going to apply that to the total insured value across each of the almost 13,000 zip codes that are affected by hurricanes, and sum them over those zip codes to estimate the total loss to a particular portfolio of property that's insured by a particular firm. So here are the centroids of the zip codes, almost 13,000 of them. Together, the property in these zip codes that's insured by this particular insurance company is worth about $2 trillion. Okay. So what's the result of that exercise? Well, here's sort of a bottom line. We're looking at the annual probability that this insurer is going to lose the amount of money on this x-axis, the bottom axis. Now, it's logarithmic. So, I mean, these are minute amounts, not even worth talking about. 10 to the 0 means $1. Okay, it's not very important. Now we're up to 10 to the 5th, which is 100,000, 10 to the 10th, which is 10 billion, and so forth. And this black dash line is the total value of all the properties. So this is the annual probability of exceeding this amount. The blue is for the climate of the historical period. The red is for the climate of the last 30 years of the current century. And the shading shows the scatter of the estimates from these 8 climate models. And it's tolerable for the present, but really large for the future. There's a lot of uncertainty just from climate models themselves. They're all over the place. All right. But there's a big gap between the means here, which reflects the climate change that's occurred. All right. So there's much higher probabilities of loss, particularly at the high end here. So how do we interpret that? Well, if you look at these curves, it turns out the median annual loss, that is in some sense the loss you expect in any given year, because hurricanes, after all, are rare. We call that the 2-year return period loss, is only $12 for the historical period. It means most years nothing happens. Okay, that's really what we're talking about. By the end of the century, it's up to 3.5 million, this median loss. Okay, but that's not the basis of insured value. We want to look at the average annual cost over a long stretch of time. And to do that, we take this probability and multiply it by the loss itself to get something called a loss density curve. Now, you don't need to know very much about this, but the same format. Blue is for the historical climate. The red is for a future climate. Shading shows the scatter, which is enormous. Black lines, the total insured value. What you need to know is that the total cost, or the average annual cost, take the total cost over a very long period of time divided by the number of years, and you get the average annual loss. It's proportional to the area under these curves, and you can see that that's increased a lot. So the average annual loss for the historical period is about $500 million, $500 million, but a big range of estimates depending on the climate model. And by the end of the century, it's up by almost 3 orders of magnitude to 4.1. It's up by a factor of almost 8. I misspoke, about $4 billion, but with a really, really large range. There's a lot of uncertainty. We haven't even talked about the uncertainties of the downscaling. This is just the raw uncertainty of the climate model. So this is what we're up against when trying to estimate the costs of action or inaction about the future. So the really important thing is that most of the area on these curves in the right-hand diagram is coming from very, very high loss events, which, if you look at the left diagram, are very low probability events. So the average annual loss, particularly in the current climate, that's the climate we're more or less adapted to, is dominated by very rare events. And that makes it very hard to convince people to do anything about it. And you're likely to miss the really big events because history just isn't long enough. Now, economists who specialize in climate, like Solomon Siang at Stanford, have tried to sort of sum all these damages over all the possible things that can go wrong because of climate change, not just hurricanes, but all the other things, wildfires, uh, human violence, even. And these are estimates, and with colors depending upon the emission scenario, with the red colors being very high emissions, green being very low. Graphing the direct damages, this is to the US economy only, by the end of the century as a percentage of the gross domestic product at the end of the century. So these damages are graphed as a function of temperature change. You can see by these error bars, there's a heck of a lot of uncertainty in this. But by and large, on average, a 3-degree change, which is sort of a middle of the road estimate, would be 2% of the GDP every year. Now, there are a lot of people going around saying, oh, 2%, well, that's nothing. We can handle that. That's no problem at all. 2%, 3 degrees. Why are we doing anything about this? Well, it turns out 2% is a huge number. And to put that in context, we're going to look at the history of real GDP per capita in the US from 2000 to 2017. It's an increase, generally speaking, over the time, but with some very interesting perturbations. So we have this drop in the 1930s, corresponding to the worst depression in the last 200 years or so, 150 years or so. And on average, it was less than a 2% drop, but it was sustained for about 10 years, okay? So 2% is associated with a really horrible depression. It's not a minor thing at all. But you have to remember that this 2% change is sustained or compounded over many years. It's not just 1 year. And the co-author of the paper I've been quoting from says that most people just don't appreciate that. It's a few percent per year, every year. There's another aspect of this graph, which is worth commenting on, which is that there was a little peak in this curve in the 1940s, corresponding to World War II, when the US spent 40% of its GDP on the war effort. And this sort of disproves the idea that if you spend a little bit of your GDP combating a big problem you have, you're going to crash the economy, all right? And lots of people get upset when we talk about spending 2% of our GDP to combat climate. In the war, we spent 40%. The other thing to note about these estimates is they fall disproportionately on the poor. So this is projected economic damage from climate change in the US. It's damage relative to county income for each county and classified by how wealthy the counties are. So the poorest 10% are on the left, the richest 10% on the right, and you can see there's much more proportional damage, although again, with big error bars in the poorer counties. So climate change does affect the poor disproportionately. Now I want to turn to the next subject, which is very much at the heart of the energy of the climate problem, which is energy. It's all about energy. It's the production of energy, its use for the most part, that's responsible for this problem to start with. And so one thing that we could do to try to mitigate that is to transition to clean energy. So what has been the response so far? Not very encouraging. So this is a chart from 1990 to 2015 showing primary energy consumption globally by source. And these curves at the bottom are all fossil fuels, the low carbon contributions, this ribbon of yellow, blue, and orange at the top, okay? And maybe the growth has slowed, but it's still growing, okay? Emissions are still going up. And from fossil fuels. So we're nowhere near solving this problem at the moment. That's the bottom line. Now, before we get into rational responses, I think it's fair to examine what I call the political priors that are preventing an objective response to this problem. And I've divided them fairly crudely and not very accurately to right versus left, if you don't mind. So from the right, I've just pulled an example from a Investor's Business Daily. As we've said many times, evidence continues to show weaknesses in climate models used to predict future warming, nor have various calamities that were supposed to have occurred by now materialized. Well, that person hasn't been reading the newspaper about fires and storms and floods. So the translation is that as far as somebody like that's concerned, no, there's no risk. There's no problem to solve. What are people worried about? Okay. And there's all kinds of disinformation in the statements, like, for example, the implication that the only evidence we have is from complicated models, which I've shown you from Arrhenius's work, and from observations is just not the case. But there are all kinds of other inaccuracies. But it's not just coming from one side of the political spectrum. Here's an interesting, but I think very representative statement from a leftist organization, the Massachusetts Sierra Club. Interesting statement. Climate change is an existential threat facing humanity and many other species. Okay, let's take them at their word for that. You might not like such an extreme phrasing, but there you go. The goal of fully transitioning the world's energy mix toward renewable energy sources is no longer a utopian ideal. It is being achieved in a number of places around the world today. Now, let's deconstruct this a little bit. The goal, as is very explicitly stated, is not to solve the climate energy problem per se. It's not to address some of the other problems like poverty or population. It's to get to renewables, okay? Why is that? Why do they exclude carbon capture? Why do they exclude nuclear? This is their thing. They want to go to renewables, and at least they're being completely upfront about that. So now let's talk about the sort of the numbers behind this. What is it really going to cost to decarbonize energy? I've decided not to put into this mix the costs of possibly extracting carbon from the atmosphere. That's a real thing and should be talked about. But I'm just looking at cost to decarbonize energy. Now, the first statement of reality here is that by 2040, we're going to need 5 trillion watts generating capacity globally. That's a lot. It's more than twice what we're using now. Why is that? It's because of hope for growth in energy in relatively underdeveloped places like India and Equatorial Africa. It is, as I'll show you in a minute, key to lifting people out of poverty. So let's suppose you want to do this with just renewable solar and wind. And I'm not suggesting you should want to do just one source, but we'll take it one at a time. It's very cheap and getting cheaper to buy solar and wind if you don't think about storing energy from times when you're producing it to times when it's not being produced, like night, for example, or times when the wind isn't blowing. If you are realistic and don't have priors that are warping your judgment, for 12 hours storage, it's about $4,000 per kilowatt hour with the cheapest means of storing energy currently available. And that's actually a projection for the year 2025. And so if you want to replace all of the capacity by 2040 with this, or you want to have enough storage to do this, it's going to cost you globally about $1 trillion per year for 20 years. Unfortunately, the current lifetime of a lithium-ion battery is only about 10 years. And so that's another $2 trillion in maintenance costs. That only gets you 12 hours of storage globally. Okay, it's not enough. It's going to be very, very expensive if you want to do this. It doesn't cost anything like that today because it's only a small fraction of the grid, and it's being backed up mostly by fossil fuels. All right, it's if you try to get away from that backup that you get into trouble with the numbers. Nuclear fission can be ramped up in 10 to 12 years. How do we know that? I'm about to show you because it's already been done in a few places. We'd have to build 125 2-gigawatt reactors. That's sort of a moderate sized reactor of the current generation per year for 20 years. And if you look at how much it costs to build one of them in South Korea, who are building American design pressurized light water reactors, it's about $4 billion per reactor. So that you need to spend $500 billion per year, or about 0.6% of world domestic product for 20 years. Still very expensive, but nothing like the cost of going solar and wind alone. And as I mentioned before, if we look at the amount of energy added per person for any 11-year period in which of the most rapid growth in nuclear energy in the past, Sweden and France, in particular, completely decarbonized their electrical production in about a dozen years, mostly with nuclear, but also hydro. Those are the two main sources in both France and Sweden. It's been done. Okay, Sweden today, France today, hardly any fossil fuels and hardly any wind and solar either, by the way. It's mostly hydro and nuclear. But an environmental organization, the Sierra Club, is unequivocally opposed to nuclear energy. And that now we have disinformation coming from the left. We've seen 3 serious disasters: Chernobyl, 3 Mile Island, Fukushima, catastrophic damage to land, human health, and our food supply. No, there was only one of those 3 which had any serious loss of life. That was Chernobyl, okay, if you actually look at the data. And if you look globally at mortality by energy source, coal is king, okay, and oil and gas are closely following. Then you go down the list: hydro, solar, wind, nuclear. Nuclear is hands down the safest source of energy we've ever generated, in spite of what you've heard. That's just what the numbers say. Now, in the United States, we tolerate 13,000 premature deaths per year from coal production and combustion. And around the world, it's 8.7 million. Now, if we had any of these other energy sources, like gas, for example, or solar, that produce this outcome, it would be shut down overnight, okay? But these are numbers, they don't lie. And the sad thing is, pace the Sierra Club, more people die every 3 days around the world from particulates owing to fossil fuel combustion than have died in the whole history of nuclear power. And that was from a plant whose design was defective and will never be built again. Those are the numbers, and they do not correspond to reality as recorded by people with very strong political passions. Now, if you just take the numbers of what we have done in the past, not just guesses about future, what France and Sweden did, we could decarbonize electrical production in 30 years. Without too much effort, if we had the will to do that. Now, I want to turn finally to the subjects of energy, population, and poverty, try to build these 4 threads that I mentioned earlier, try to bring them together. One thing that we see as an empirical truth is that per capita emissions go down as per capita income goes up. And this is from data in Sweden. Carbon emissions per capita from 1950 to 2015 or so, they went up initially, and then as Sweden decarbonized, the emissions went down, but the national income per capita went up. All right, so decarbonizing does not have to mean a decline in income per capita. In fact, in most places, it was accompanied by an increase. But this is a key point now to poverty: is access to energy is absolutely fundamental to lifting yourself out of poverty. This chart shows electricity use per capita versus some index of human development. You don't have to really get into that. You have a little bit of a inlay here that shows you what went into this, but qualitatively, you can see that the less developed countries are using a lot less electricity per capita. And in fact, countries which lifted themselves out of poverty, like China, are lifting themselves. That's accompanied by a big increase in electricity use per capita. All right. Almost 1 billion people on the planet today had 0 access to electricity, which is pretty shocking. If you're really serious about poverty, you're going to have to increase, not decrease, per capita energy consumption, at least in those countries. And we can't ignore that problem. And control and this business about lifting people out of poverty empirically is a key to controlling population growth. And population growth is a big factor behind the growth in emissions. All right, so it comes full circle. So if you're really serious about population growth, controlling population growth, you've got to accept that per capita energy consumption will go up if you're serious about doing that. Let me wrap things up now. The climate problem is difficult because event probabilities, societal costs, and mitigation costs are all continuous. They're not binary and very uncertain. The beneficiaries are distant in space and time, and decision-making is hobbled by lots of priors on both sides, on all sides, you might say, of the political spectrum. Tail risk, that is the improbable outcomes, extreme outcomes, is probably existential. From the right, global warming, I'm being a little bit cynical here, is an excuse by Al Gore and his buddies to implement long-term leftist agenda of socialism and big government. It will cripple the economy. I'm amazed by the number of people who think that way. From the left, the goal isn't to solve poverty, global warming, it's to get to 100% renewable energy, which empowers people and cripples the fossil fuel industry. We got to go get those fossil fuel people, right? Nuclear is scary and an example of big business and must be avoided at all costs. This is sort of, I've talked to a lot of people who more or less say this. But deployment of judicious combinations of renewables, carbon capture and sequestration, which I did not talk about, and nuclear power can mitigate climate at a reasonable cost. And it can happen fast if we can only get over our priors. Rapid increase in affordable energy in developing countries is imperative to increasing per capita wealth and decreasing population growth. And I will leave you with that. Thank you very much. And sorry, I can't be there to talk with you more about that. Bye-bye now.